Okay, so I guess we can begin. Is this fine? Everyone can hear me? All right, perfect. So I'm Norbert, and this is Babel Fish is Data. This is the Babel Fish from the Hitchhiker's Guide to the Galaxy, which teaches us two things. Always bring a towel with you when traveling internationally, and that a Babel Fish is a really useful device because you put it in your ear, and it translates all alien languages, right? It's like this ideal Google Translate combined with Siri. The hypothesis of this entire talk is data is the Babel fish of programming. That if we were to focus on data instead of on functions, objects, microservices, and all this other crap, then we would just build better systems. I changed my talk. I threw out all my slides, and I'm going to talk about something slightly different. So I can't talk about this, but come to me at the after party, and I'll tell you all about scurvy and why it's relevant. And also, or if you prefer, there's an online version of this talk on YouTube right now that talks about scurvy and has a bunch of programming slides, code slides. Because instead of talking about code, I'm going to talk about design. Some words of wisdom. This actually is very good advice, which is that if you want to design something well, you take it apart, find the essence of things, and then put it back together. And that's what we're going to talk about today. How do you take apart information systems and put them back together? We all build information systems. I mean, at least I spent my entire career building information systems. I expect most of you build information systems on a daily basis. The way I define it, an information system is it's this big black box. That's your system. And there's chaos outside, and that's the real world. And your system only does two things. The first thing it does is it takes data that comes from the outside world, you know, like these events that we keep talking about, and stores it and gives it order. Your job number one is to store data securely, because if you lose your data, you can't get it back. You can't generate user data once more, right? Because it came from the outside. You have no idea what it was. And the only other thing your system is supposed to do is some point later in the future, a user comes along and asks for data, or a machine comes along, or someone requests an API makes an API request. And so maybe you munch the data around, you create some aggregations, you do some analysis, and you spit out a golden egg. And that's what an information system is. It's a way of just eating and pooping out golden eggs over and over again. And if we realize that this is basically what we do for a living, it turns out that there's a lot of neat ways we can talk about these systems and decompose them. One way is to talk about shape of data. Your system only has three kinds of shapes. It has streams, trees, and meshes. A stream is just a semantic that there is an order to data, right? This could be some kind of bounded queue or an infinite generating stream of prime numbers or anything else. The only semantics you have is that there is an order to the data. The next kind of shape of data is a tree. The most common place where you see trees is your UI, right? Whether you're building web apps, mobile, desktop, whether your system is generating CSV files, Excel reports, or you're just an API backend response that's serving JSON, it's all trees. And if your libraries and your frameworks let you work with your data as a tree, then it turns out that a lot of nice properties just fall out. And the last thing is graphs, and specifically meshes, which is a kind of graph. And that's your business data. Right? The way I define a mesh is that you have, like, your business domain basically has only about, I'd say, 3 to 5 core objects. If you disagree with me, come after the talk and I'll prove you wrong. Let's take Spotify for an example. Spotify has listeners, artists, and songs. That's all it has. Any feature you add to the system is a new relationship between existing nodes in the graph. So when I create an album feature, what I'm doing is I'm creating a relationship between an artist and a set of songs. And I'm attaching some metadata to it, like what is the title of the album. When a user creates a playlist, it's a relationship between a user in the system and a bunch of songs with some metadata attached to it. When I create a feature called, subscribe to someone's playlist, I'm creating a relationship between a listener and that playlist I just created in my system. And what happens is, with every single feature you add over time, your data mesh, your data graph becomes more dense. More and more dense. With every single feature you add, there's more relationships interconnected with each other. And sooner or later, you get this really dense mesh. And this is one of the fundamental problems with the way we build systems, because if you model your business data as, for example, a relational database, then with every feature you're adding, your you're trying to figure out a way how to take a relational query and do graph traversals on it, right? So you end up with a bunch of n+1 queries, a bunch of weird SQL joins that just aren't performant. And if your response to this unscalability is, let's do microservices, and the way you do microservices, you now have a bunch of services, and each of them has a subset of the database, like its own independent database. What you've done is you've taken that same monolith approach that didn't work, and you've distributed over the network. Now all of your n+1 queries and your joins are over HTTP. So in fact, they're even slower than they were when there was a monolith SQL database. The realization is, the important thing to understand is that these are the only shapes you should care about, and it doesn't matter what programming language you use, it doesn't matter what architecture you decide to work in. You need to ask yourself this basic question: does my system allow me to represent data in these three shapes and to easily switch between them? Right? Can I take a stream, convert it to a tree, and then do graph traversals on it, and then convert it back to a tree to spit it back out? If you can't, sooner or later, your system is unmaintainable, and you do the, like the major rewrite, right? But it never works because you're going to end up doing the same mistakes over and over again. A different way of decomposing information systems is to just realize that anything you build is a distributed system. And it doesn't matter if you're Google scale and you've got millions of machines distributed over geographical regions, or you're building a mobile application that doesn't even talk over the network. You have created a distributed system that reacts to events in like user clicks or whatever it is. And the only thing to understand about distributed systems is that the components of that system need to communicate with each other. And the realization is there is one thing that works well for communication over the wire, and that's data. Because data represents itself. So when you serialize data and then you deserialize it back, you get back the same result that you sent, right? Data represents itself. It doesn't have implicit context. What does have implicit context? The objects in your system, right? This is why you have that impedance mismatch. When you have an object-oriented system and you try to serialize it on the wire and get it back, in an ideal world, you would have to serialize the entire runtime because objects have context. They don't represent themselves. They represent themselves at a specific point in time with a bunch of unrelated stuff, right? This creates an impedance mismatch. Yet another way to talk about how do we decompose a system is to say, well, I know there's separation of concerns, right? There's different kinds of things in our system. And I'm not talking about MVC or REST or even CQRS. I'm talking about one-way data flows. Anybody heard this term before? Some very few hands go up. Awesome. So the idea is, so here's a pattern, and then we're going to see how this pattern can be applied. So the pattern is that you have events, right? That's the introduction to your system. That's the chaos. And events enter into your system, and they always enter via a log. The log is responsible for giving an order to the data and to store it securely, right, as flat data. After you have stored all this data securely in an append-only log, there's a transformation process that basically takes all of the data in the log and creates some kind of temporary caching, materialized views that are there to sort of allow you to do performant queries. So there can only be one log in your system. It's a single source of truth, and it's a single entry point into your system. But there can be many views, many different ways of talking about that same data, and many readers, many people that are querying that data at the same time. Because it always flows in one direction, you don't have that whole problem of updating and atomic locks and all this kind of other stuff. So that's a pattern. How do you use it? Well, if you want to build big systems, you look at things like Lambda architecture for inspiration, right? The idea is that the events are the outside world. They go into something like a Kafka queue, right? And the Kafka queue is responsible for durable storage of all events, right? We don't want to lose user data. And then you have a batch processing process, batch processing like component. And this could be like a Hadoop or a Spark or a Storm cluster, or like a set of microservices that take a bunch of data from Kafka and then create a bunch of views. And in the case of big systems, those views are actual databases. It's things like Elasticsearch, SQL, maybe a data warehouse, or some kind of graph database. The idea is that you optimize the kind of queries that your users are interested in by creating read-only databases. But the source of truth is always that single queue at the top. Lambda architecture also has this thing called the speed layer, which I'm not going to go into, but it basically uses that same data source Kafka to sort of take a second approach if your batch processing is not fast enough. It doesn't change the model. If you're interested in it, I highly encourage you to go read more about it. Datomic. Datomic is saying, let's take this exact same pattern, but apply it to how would you build a database? So the Datomic team figured out that a database is 3 separate things, right? Find the essence of things. And the things for a database is, it's a storage, it's a transactor, and it's a bunch of peers. The storage mechanism is, we want to store this data somewhere, but we really don't care where you store it and how you store it. That's use case specific. So we're going to give you an interface. Here's the interface for our storage mechanism, and you store that data wherever you want. It could be a Cassandra, it could be a SQL database, it could be flat files, it could be an in-memory database if it turns out that you don't really have that much data and you really don't care if you lose it, right? A transactor is, again, that same queue concept of a single point of entry into your system. And the peers are those materialized views that create temporary indices that, based off of the storage engine, that are used for the queries. And what Datomic does is it says the input into our system is this really interesting 4-element tuple, entity, attribute, value, time. It turns out that this is a wonderful data structure because you can model anything using that data structure, whether it's some kind of identities, it's collections, it's graph traversals. It turns out that you can model everything just using those 4-element tuples. And the queries, on the other hand, are using data log, which is a graph traversal. So you have graph queries on the output, but you have the input, it's a flat data structure that's a log, right? And then the peers can scale horizontally as much as you want because it's just read-only. What about a web browser? Well, it turns out that you can use the exact same pattern. Omnex, if you're not aware, is a ClojureScript library that is a library that sits on top of React. It's very similar to what Facebook does with its Relay and GraphQL. And it's, again, the exact same pattern. The pattern is that we have a queue. In the place we work, we use DataScript as in the web browser, so we use that EAVT structure, again, as the input. The events into a system are everything, right? It's whether the user clicked on something in the web browser or the HTTP response returned a value or something got pushed by the server, like via WebSockets or server-side events. Everything enters that exact same queue. There is only one queue, at which point indices are built based off of all that data in the queue that is then used to do graph traversal queries. And those queries return business data using a graph query which hits the render function. The render function takes that business data and returns a tree structure, and that tree structure is a representation of what the virtual DOM is supposed to be, and then React takes over, compares the virtual DOM to the old snapshot of what the DOM is right now, and does an atomic update. And this lets you do 60 frames per second updates in your web browser using a very one-way flow where it has no mutations. All the events, all the changes into the system always coming from the top, so it's wonderfully testable. You don't even have to run a browser to test all this stuff. A different way of decomposing systems is to make it explicit that there's always an information model and an execution model. Because we often conflate these two things. We put them together, and it turns out there's really nice properties that fall out if you make them separate. So, a good way of designing systems is to imagine that you have this information model that's the base of your pyramid. And most of the work that goes in is to figure out what is the information model of the thing I'm building. Because it turns out that then all of the assumptions that you put into the model perpetuate up into the API, into the DSL. So you create a model. That's where you do all the hard thinking, like what are the constraints of my system? On top of which you put an API, and all the API does is it says, these are the common practices for how we should manipulate and use this information model we built. And then sometimes it's convenient to create a DSL on top of that just does here are the common practices, so we've simplified some of the usual scenarios. But whenever you're interested, whenever the DSL doesn't do what you want, you can always look at the API, and if you realize that the API is missing something, you can look at the information model and figure out what it is that the API is missing. So this is the ideal situation. Unfortunately, sometimes this is what we do. We create a huge DSL, and every time a new feature comes in because we forgot to implement something, we extend the DSL. And over time, we keep extending this DSL until at some point someone realizes that they want to do something that's outside of what the DSL allows. So you start backporting an API. You start backporting an API so you can do things programmatically that the DSL doesn't allow. And once you start doing that, you realize that you can't really create a DSL if you don't have an understanding of what the underlying model is, right? So you start backporting the model. The problem with this approach is, if you didn't think about it in the DSL, the model probably doesn't support it, right? You didn't think this through. But there's an ugly version. An ugly version is you just have a DSL. The DSL has become so complicated you can't create one API that manages all that complexity, and there is no information model. Every single person working on the DSL had a slightly different idea of what the model is, but it was in his head. And people never got together to talk about what it is that, how they understand that this model should work. SQL is an example of that. SQL is a string API, a string DSL, right? And the best part is it's not a string DSL because every single vendor has a slightly different version of what SQL means to them, right? And the best part is they never bothered to create an API, so the first thing you do in every single programming language is create a library that takes a string, tries to parse it into a data structure, manipulates that data structure, pushes it back into a string, sends it to the SQL engine, only this time it has a SQL injection like hack in it, right? Because by accident. Or worst case, you don't even create a data structure to manipulate it. You try to interpolate strings, or you do like regular expressions, right? That's your API to your database. So there is no API. No vendors got together to sort of figure out what the API is. And there is no relational model because there's something called COD's like 12 or 40 rules. Sometimes it depends which one version you want to listen to. But the problem is that it's something that came after the fact. Like after they built these databases, COD was like, you know, we should probably try to figure out what is the information model that we're working off of. And it turns out that none of the actual like production ready databases actually use this model like 100%. Datalog is an example of like the exact opposite of how you can create a query language, because Datalog is a subset of Prolog, which has very strict rules about what it is, because Prolog is just a first order logic programming language, which actually sits on top of pretty sound mathematical predicate logic and set theory. So anytime you're wondering what should Datalog do in a specific case, it's really easy just to look at the math, right? What is the mathematical model that this is based on, and what does that mean for what the end result should be? Java is actually a really good example of how to build systems like this, because you have Java, which is a DSL. The DSL is just a DSL for JVM bytecode, which is a much smaller set of instructions that are actually pretty sound, that sit and run the JVM runtime. Now, we know this model is pretty good because we can take that really terrible DSL and replace it with something much better, and everything still works, right? And we know Clojure is a really good DSL because the guys that built Clojure, specifically Rich Hickey, thought about it as a DSL that runs on a different platform. And so it turns out that the DSL works on multiple platforms without any changes, right? That's the definition of reusable code, right? A JVM can run multiple DSLs, and a DSL can run on multiple machines. This is like what we should be striving for in everything we do. The last thing we want to talk about when it comes to decomposing systems is about business domains. Because I have a really dirty secret that I think we all know, but we don't want managers and CEOs and C-execs to know, which is that programmers are really good at dealing with shitty software, right? It's amazing how much crap we put up with, like the amount of complexity we can keep in our heads to keep this really weird spaghetti mudball of what we call our legacy system up and running at all times. Now we're gonna complain all the time about how this is terrible and needs a refactor, but every day we come into work and our systems have not crashed. Our business has not gone out of business. It says something for our ability to keep really weird complexity in our head and disseminate enough to sort of keep it running. So it turns out that when projects fail, it's not due to technical or the lack of technical excellence, right? We all have shitty software. We all have these dirty secrets and this dirty laundry, and it's all still running. The reason projects fail, and really the only reason projects fail, is you end up building the wrong thing. And usually you build the wrong thing because you don't understand the domain you're working in, right? You don't understand the domain, so you end up building the wrong thing. And by the way, this is what makes projects fail, because if you build the wrong thing, no amount of beautiful code is gonna keep the business up and running. Or sometimes you understand the domain, but you don't model it correctly. Like you make a mistake. You'll realize after the fact that you had the wrong idea for what the model of the domain was, so you ended up building the wrong thing. Or what sometimes happens is you think you're doing a good job. You understand the domain and you've modeled it correctly, but somewhere down the line the business changes, or the environments change, or you realize that, you know what, you were actually mistaken about a part of this model. And this is usually what we really mean when legacy fails. It's that we realize now that the model is not correct in some way, but we are not agile enough to pivot and actually fix it, right? We're not good enough to make sure that the system actually models the domain we're working in, and so we break the company. But it turns out you can actually use this same diagram to model your business domains. So a good approach is to basically use the information model as the basis for all of your decisions about how we're going to build this thing, on top of which you build an API that says this is the way we're going to manipulate this model in our applications, on top of which you build an UI, right? And then everything's honky-dory, except we never do this. What we do is we imagine an application, a UI, right? Someone comes up with an idea for a startup. He's basically doing that thing. He's doing that UI part. The UI drives the API decisions, because the API is there just to figure out what the UI should be displaying. And then the API drives the information model. So anything we forgot to think about when we were designing that application never trickles down to the model, right? And so things are gonna end up getting broken over time because we're not modeling reality. That's actually not the worst part. This is the ugly version. The ugly version is that you allow developers to be product developers, and they create a REST API that's a backend. And the REST API actually, this is insane when you think about it, actually drives what the UI is supposed to look like and work like, right? The backend developers say, this is the REST API we created. Now you make a UI that works with our API. And there is no model. There is no model. Basically, the database is just a one-to-one correspondence to what URLs we decided to make up when we were developing the REST API. So, I've covered lots of weird models and stuff, and the question is, how does this relate to you? Like, how can I take these ideas and sort of apply it to my daily work? And so the answer to that is that we come back to our hero. Our hero is data. It turns out that if you start to learn how to decompose systems into basic data and start communicating with everyone and with your systems, with your coworkers about how data flows through your system, then a lot of this stuff just sort of falls into place. Data is really simple, by the way. It's just information at rest. It has 3 properties. It's supposed to be immutable because it's information. Information doesn't change. It's just facts. That's all it is. There's nothing controversial about this. Information is just immutable by definition. But the kind of information we want to work with is semantic. We want to figure out what are the basic building blocks of our system, and the way we do that is we figure out what are the semantics we're interested in. If there are 2 things that can be represented by the same semantics, they're not 2 things in our system. They're just one thing. And since we have a limited number of building blocks, we need recursion to be able to build big systems back up. So that's kind of abstract. Let's look at some examples. So I'm going to prove data by example. So data is scalars, things like numbers, strings, Boolean, identity. Maybe there's a couple more semantics you might be interested in, like instance of time, a global unique ID, right? There's not that many of them. There's only a handful of them. And there's really just 3 collections. Right? There's just lists, maps, and sets. Lists give you the semantics that things are ordered. Maps give you the semantics that things have association. And sets give you the semantics of mathematical sets. If you want to split hairs, you can say that things are homogeneous and heterogeneous. So now you have 6 kinds of collections. So, closure. I'm going to show you some little closure. By the way, it doesn't matter if this is closure. All this stuff exists in your favorite language. You have scalars. You have things like numbers and strings, Boolean, nil. Closure has 2 ways of talking about identity at a data level, and that's symbols and keywords. And then closure has collections, right? Lists give you the semantics of order, maps give you the semantics of association, and sets give you the semantics of a set. 2 caveats. Caveat number 1, why are there lists and vectors? You said there's only one kind of thing. Well, it turns out there's one kind of semantic for, yes, this collection has order, but it also turns out that there's a lot of data structures we use on a daily basis. These two ideas are not conflicting. The idea is that you can replace a collection, some kind of data structure that provides you semantics of order with a different data structure that provides you with semantics with order without breaking your system at a fundamental level. The only thing that changes is performance characteristics. So it turns out that there's lots of data structures because you have various kinds of performance characteristics and trade-offs you make on your daily work. The second caveat is maps. Because maps are not one thing, they're actually two things. Remember we were talking about heterogeneous and homogeneous? The top map is a representation of a bag of data. It's just a bunch of key attributes and values that represent a profile. The bottom map is a index of usernames to favorite language. It's a very different kind of semantic. And you use those two semantics for very different things. So everything we've seen up to this point is what you have in your language of choice. The thing you might not have unless you work in a Lisp is that you don't have S expressions, right? So this is the thing that makes Lisp Lisp. It's the idea that a Lisp has a data structure of a list. The first thing is a verb, the rest are arguments, so you can evaluate it. But you can also quote it, which means that it just returns the data structure that it represents. And because it's a basic data structure, it means you can do operations on it, like count how many things are in the S expressions. Hands up if that doesn't make sense to you. I mean, right, perfect. You are all now smug Lisp weenies. Congratulations. How am I doing in time? Perfect. Okay, so we all now know Lisp. So I have a thought experiment for you. If I told you that I'm going to choose one of these languages and you're going to have to work with it exclusively for the next 6 years, who here has a strong opinion about what language that would be? See like everyone nodding their heads. Kotlin doesn't exist. That means you have an opinion. You're just proving my point. So everyone has an opinion about what language they would work in. Now the question is, do you have that same strong opinion if I told you that I'm going to arbitrarily choose what data language your system supports, right? Not so much, right? And I mean, if you think about it, that's really weird because we've been talking about all these microservices and all this other stuff, and that means that theoretically you should be able to replace a service with a different service written in a different language at any point in time. But the one thing you cannot take back is if you decide that the data language of choice in your entire system, in your company is JSON. Like you can't take that decision back because if you decide that JSON is the language to go, and then you end up deciding some point later in the future that JSON wasn't it, you have to replace everything, right? Nothing works because data is that thing, is that glue that connects everything you've built. So it's amazing how little we think about the data language choice we make because if we choose something like JSON that doesn't have an idea of something like a date time, then, or sets, then we have to live with that decision for our entire lives, of the project at least. I personally work in Clojure. And when people ask me why I work in Clojure, it's because you all have your favorite language of choice, but Clojure is not a language, it's the Borg from Star Trek. Because the way the Clojure works is you have your pet language, and your pet language has some awesome feature, like CSP or types or whatever it is. And that's nice and dandy, and you start making some talks about it, and everything's fine. But in 3 to 6 months, we also have your favorite language feature, right? Clojure doesn't play fair. What Clojure does is every time you come up with a really good idea, we steal it, right? And that's the beauty of Clojure. It's that I can always keep up with you. It doesn't matter how much research you put in. In 3 to 6 months, I have a library that does what you had to write a new language for, right? And that's like language semantics. On top of that, as we saw, Clojure has a DSL, and the DSL means that I can run on multiple systems. So I get all the same benefits in JavaScript without any changes whatsoever, or on the CLR. I'm not here to convince you to use Clojure. That's not this talk. I'm here to tell you about Clojure Spec, which is the most recent thing we stole, this time from the Racket community. And this is the idea of data contracts. How do you specify things about data? How do you make specific claims about data? How do you talk about the shape of data? So Clojure Spec is one of those answers. It probably should not surprise you. I hope it doesn't surprise you at this point that Clojure Spec separates an information model from an execution model. I mean, if nothing else, I hope I've driven that point home. So the information model in Clojure Spec says everything about how it is that we specify data. It just talks about the specification of data. It doesn't say how we use it. That's what the execution model is for. So I promise that we weren't going to do code because we don't have time. So code is going to show up on the left, but you're going to ignore it. We're just going to talk about basically some examples of things that you sort of ClojureSpec provides at an information model level. So you have this idea of there's a predicate and you can give it an alias, you give it a unique name in your system. You have the idea of composition, which means that if you create two shapes, you can put them together via AND. There's OR that basically says that there's a branching concept, right? Like a data can be more than one thing, very different things, but all those things are valid. So OR just basically says, here are the valid kinds of shapes of this specific thing. You can, of course, put these things together. So here's an OR and sign an AND. And the interesting thing about the AND is like all the way over there on the right, like my red dot is like barely spinning, is that except for the fact that you have specifications, you also have data transformations. So this is an example of a poor man's either monad combined with a monad transformation. You also have collections, right? So here I'm just going to define more attributes so we can work with the examples. So we're defining some programming languages and some user attributes. And here we are creating a user lang specification, which means that my user language is a set of languages, right? So you have the idea of collection of, and you have the idea of map of, which is, remember those semantics of homogeneous maps. User lang is a map of username to favorite languages, to a set of languages I know. And keys is that heterogeneous map, right? It's that idea of a shape of a profile. A profile is nothing more than a map that must have a username and a user language and optionally has a user age, right? That's all we're defining. ClojureSpec is actually an implementation of regular expressions, so it has things like concatenate, star as in 0 or more of something, or 1 or more of something. It has the idea of recursion. It has everything you expect from a regular expression library, which means that in this example, we're actually specifying what Clojure syntax looks like, in a simplified version, of course. And the last thing I want to show you is fdef, which means fdef is a way to talk about specifying what data at runtime looks like. So here's an adder function. So like all the way on the top is an adder function. It's somewhere in my runtime, and I'm specifying shape of data for its arguments, its output, and a relationship function between its inputs and outputs. This is unnecessary from like a code perspective. If you're interested in details, go and watch that other talk where I actually talk about this stuff. So execution model. We've defined all this stuff, but it's sort of just sitting there out in space. We haven't actually linked it to anything. So the reason of separating is that you can then use that same specification for many different things. So one obvious thing is you can ask if data is valid, right? So here's some arbitrary data, string 4, and here's the specification. So valid just asks, is this valid, true, false? If it's false, false is useless information because it doesn't tell me why, so there's explain. Explain basically parses an entire shape and will tell you very precisely why a specific why a specification doesn't work for you, why a shape doesn't match. Conform is the exact opposite of explain. If a specification is valid, this will actually deconstruct and return the expected shape at the end that you asked for. So in the case of even or odd, if you remember from the previous slide, there was an OR branch. The conform will actually tell you which branch it followed to get to the data that you were interested in. And there's exercise, which is a wonderful thing when you think about it, because if you've already told your computer about the shape of data, why do you need to generate data? Why can't you let your computer generate it for you? And that's what exercise is. Exercise basically says, given a specification and some number, that's the amount of data I'm interested in. Just give me random data. The thing on the left is the input, and the thing on the right is the conform data. Here's another example of exercise. And this is, we're generating a map. Notice that age exists on the top map, doesn't exist on the bottom map because age was optional. So if we already are able to generate data programmatically, the question is, what else can we do? Well, we can do assertions about our system, which is what instrument is. Instrument basically says you run it in like development and your CI, and you created those fdef instructions, which basically talked about the specifications for functions that are in your runtime, and instrument will basically run assertions on that in your testing environment, right? So anytime you use a function, it'll make sure that you're using it correctly. And test check is even more interesting because it says, since you've already told me what these functions should accept and what they should output, I'm just going to create unit tests for you, right? So I'll just create random data as input, I'll run your function, and I'll check if the output is correct. And I'll do this hundreds, thousands, millions of times. There's no way you can write that many unit tests, and there's no way that you can come up with the weird, sick configurations that your compiler can. Which brings us to generative property testing, which is like the last topic of this entire talk. So we're almost there, we're almost there. Who here has heard of generative property testing before? Okay, like 2 hands go up. This, by the way, is Salvador Dali's painting. It's really interesting because if you're sitting up in the back, what you see is Abraham Lincoln, and if you're sitting up way in the front, you see a naked lady at a gala. TDD, right? This is like a Ruby unit test. Like you can't get more basic than this, right? What is a unit test? It has a setup. It has the input to the system under test. It has the execution of the system under test, and it has validation, asserting whether the thing is true. Notice that there's also a model, but the model is in the programmer's head when he was creating this test. He thought, there's this weird edge case when you always roll 0 bowling pins. We should probably test if the output is correct, right? The model was in his head. So you, by now, should figure out what is coming next. It looks like this thing is doing many things. We should probably split it apart, right? We split it apart, and when we split it apart, we realize that there's 3 different things going on. Given a model, I can generate random correct states of the world. And given those random correct states of the world, I can apply it to my execution model, which is the system under test, and I can generate an output result. And now given, again, some properties I want to assert about the system, I can then verify that the inputs and the outputs are related via some assertions, right? So generative property testing, so this is what you do with unit testing as well, you just sort of do it implicitly. Generative property testing says, you know what? I just need the model and the properties from you. Everything else is boilerplate, I can do that for you, right? That's all it is. The first version of this was QuickCheck that came out in Haskell. And by the way, QuickCheck is such a phenomenal tool that it is now ported to basically every single programming language. So it is already implemented in a library of your choice. Clojure as it is, the Borg has ported it, and it's called TestCheck. And what is really interesting is TestCheck is this approach applied to your functions and your modules, your runtime, like in a single process. But there's another library, it's called Simulant. And Simulant takes this exact same pattern of testing your system, but applies it to your entire system. It's like generative property testing at an integration test level. This basically replaces your QAs with bots. So, there's 2 really hard things to know about generative property testing. Since the computer is responsible for doing most of the work, you're just responsible for the model and the properties. And it turns out those are the hard parts, right? The model is that information model. It's trying to figure out what it is that we're building and how are we modeling it, right? Nobody can do this work for you. This is why they pay you the big bucks. And properties are interesting because they're difficult because they're unfamiliar. There's nothing difficult about them. It's just that we haven't been testing systems in this way, so things are unfamiliar. So what I wanted to do at the end of my talk now is show you some properties, some common patterns for property testing to sort of get your brain working in the right direction. The most basic pattern is that there are operations in your system where if you do it once or you do it multiple times, the same result happens. So once you sort some collection, it doesn't matter how many more times you sort it, you should always get back the same result. Agreed? Agreed. But it turns out that generative property testing is really good at finding bugs because it'll generate really weird data and it'll find that really weird edge case where your sort is simply unstable, right? It's amazing. It's amazing the kind of things this thing will find. John Hughes managed to find a bug in the Erlang virtual machine that existed for like 5 or 7 years in production systems. Nobody could figure it out. And the compiler found this really weird latency bug. Like it honestly generated weird cases that enforced latency, and it gave them a reproducible test case that they could actually check that they fixed the bug after like 5 to 7 years of Erlang randomly crashing and segfaulting in production. Another kind of operation is sometimes it's hard to test the system. Like how do you test reverse? Assuming that the input to reverse is random, there's no way you can assert what is the output of like reverse, right? It's the exact opposite of whatever it is. But it turns out that you have another kind of property, which is that if you reverse something twice, you should get back the same result. And so there, yet again, is a different way that we can think about how to test systems. There are many operations in your system that you can do twice. And if you want an example of this, your serialization library of choice is exactly that. Given some random data that I generate in my system, I run to JSON on that, and then I run from JSON on that, and I better get back the original input, right? It turns out that once you start thinking in these kind of frameworks, there are a lot more properties about your system than you realize at first. Sometimes functions or systems are hard to test because they're complicated, right? Like, how do you, like, imagine I wrote a better sort, the faster sort, and it's a huge, complex algorithm. You can't unit test that. You can't unit test that because you don't know the weird edge cases. But you can actually test it against a baseline. So if I was to write a new sorting algorithm, I would say, generate millions of samples and make sure that my fast sort works the same as system sort, right? Or imagine you're doing this at an integration level. You're testing an API. Someone tells you to refactor a new API, and you're smart, so you don't refactor an API in production. You create a new API endpoint, and you want to deploy it into your cloud infrastructure. How do you test that? Well, you can write as many unit tests as you want, but the truth is, the only way to test an API and to make sure it works exactly the same way as the old API is to deploy it into your infrastructure in stealth mode and let it run. And the way it works is the old API still handles all of your production requests, but you also route all those requests to your new API. And you always make sure that both APIs always return the same kind of result. And you can run this for a day, a week, a month, and basically you're given some measure of assurance that for the last month, the new API always responded in the same way as the old API, right? Sometimes things are just hard to test. I mean, it's really hard to come up with property testing for some things, but it turns out that there's properties about your system as a whole that you can test. And so the idea behind this is have a list of all possible operations on your system and write a bunch of generic properties about your system as a whole, and then sort of merge those two concepts. Just have your computer generate random universes where certain operations happened, and just run this over and over again, and every time, after every test, check that all of the properties that you assert about your business are always true, right? If I'm a UI guy, and I'm writing I'm working at Facebook, a very basic property about Facebook is that friendships work two-way, right? You can't be a friend to someone without that person being a friend back. So you just write a property about that. You write an assertion. Facebook is always two-directional. Friendship is always two-directional. Perfect. You write a bunch of assertions like this, and then you write a bunch of operations. The operations are things like, here are the things that the user can click on. Or you imagine like you're a chaos monkey that's just clicking and generating events. Maybe you're even modeling the fact that there's like WebSocket data that's coming in randomly. And you generate a random pipeline of information. And you run it against your system. And a weird thing happens. At some point, your unit test your testing system comes back and says, there was an error. Here's the reproducible case. When this, and this happened, this widget had a friendship count of 5, and this widget had a friendship count of 4. Even though the business rules of your system, of your reality, say that friendships are always bidirectional, there was some local state in one of your widgets that in some weird edge case did not update correctly. These are the kinds of things we're looking for, and these are the kinds of things that unit tests will not solve. These are the only kinds of things you can solve if you work on your information model and you work on the kinds of things that your system allows. And this is my favorite test of all. How do you test distributed systems, right? How do you do that? Well, here's one pattern you can do. So remember we had that list of, here are all the operations that are allowed in my system. Let's take that list. Let's generate a timeline of events. Here are random things that happen in my system. You have a stream. Now what you do with this is you say, imagine a universe in which there were 5 actors, and those 5 actors pulled events in order, randomly, right? So actor number 1 ended up doing operation 1 and then operation 5 much later in the future. Actor number 2 did operation 2, actor number 3 did operation 4, 5, and 6, right? Whatever it is. You basically have a sequence of data that's flat, and then you have a universe where there were multiple actors doing those operations. And you take this universe and you multiply it. You create 10 universes, 20 universes, where the number of actors are different, or the delays between operations are different, or you can generate various kinds of weird permutations. And then the question is, what can you assert about that kind of system? Well, you can't assert obvious things like X will be 3, because the input data is completely random. But what you can do is take each of those universes that had a distributed pipeline and merge them back together into a flat structure, right? Pretend there's a specific timeline of events and take those actors and flatten it. And if you do that with multiple universes, you can assert things like, I generated 10 versions of this universe and all of them were eventually consistent, right? It's amazing the kind of things you can do when you build tests in this way. And you can actually test distributed systems, which is something that people said is not possible. And John Hughes has some good talks about this. This, by the way, is the way he found that bug in Erlang. And he has a talk about how Dropbox is losing your data, using exactly this model to show how Dropbox is losing your data when it syncs. I'm pretty much done with my talk. I had a couple slides at the end to sort of maybe push you in the right direction to learn more if you're interested. I had a talk at some point about ClojureScript and React. Derek Slager gave a much better talk about why you should do ClojureScript. I had a talk about data-oriented architectures, but Martin Kleppmann is really the guy you want to listen to when it comes to how to build these kind of one-way data flows. And John Hughes has that talk I was talking about Dropbox and QuickCheck. And LearnDatalogToday.org is a wonderful website to teach you Datalog. And if Datalog is something you don't understand, then this is like plus, I don't know, plus a million to your skills as a programmer. You really should learn it. It's as old as SQL, and I don't know why it's not as popular. And this, by the way, is better than GraphQL, so learn it for that if nothing else. It'll honestly take you 2 hours with like your favorite scotch on this website to learn Datalog, except for the pull API, because this was created before the pull API. If you do this and you want to learn more, just ping me. I'll tell you what to do next. And if you've decided to ignore everything I've said up to this point, I just want you to watch this single talk. This is Rich Hickey's talk about Simple Made Easy, and it has nothing to do with Clojure. It has everything to do with decomposing systems and figuring out how it is that we should start building things in order to make them work. Don't worry about like the links. I'll tweet them out. I'll tweet them out after this talk, so you can find them. That's it. Thank you. I don't know. Are there questions? You can always find me at the after party as well. So, and ask me about scurvy. All right. Thank you.